Okay, and the problem statement for 73, it gives us this displacement map. And once we distribute it, we get the gradient in this matrix. And once we get F, for part A, it asks us to get F. And so we add the identity matrix to the gradient of U, and this is what we get. Now that we have the matrix with F, we also have a new matrix, or a new vector Z. And so for part B, it asks to compute a stretch. And here, this is the equation, and F operating on Z right here. And so once you simplify it down, it'll become this, and the magnitudes cancel, and stretch comes down to equal that, and then simplify it because the problem statement asks for in the radial direction. So this is the final answer for the stretch. Alright, so for part C, now that we have the stretch, which is up here, we have to find the Lagrangian strain with this equation, and we solve it and get it down to this general equation. For part D, we want to find the lengths of the inside and outside radius as well as the height after the displacement map has been applied to the cylinder. So we take the integral of the stretch from 0 to 1 for the inside radius, and then we get a value that is still equal to 1. And then for the outside radius of 2, we get a value of 4.77. And the height will stay the same at h, just because there is no Z3 in the initial displacement map. Alright, now that we've solved it using Cartesian coordinates, we're going to also solve it using polar coordinates. Here's the change in the coordinate system. And so now once we apply that to F, we'll get this matrix. So that's part A. And part B, we have to find the stretch again, and we want to prove that it'll be the same as the Cartesian stretch up here. So we just use the same formula, FR dotted with FR divided by magnitude squared. And then once we get it simplified, it comes out to be exactly equal to the Cartesian coordinates. So that means that part C and D are going to be the same as the original part.